Hello. Okay, today I want to build a simple Koch snowflake, which is like one of the earliest or the first fractals. So the construction of Koch fractal is, the rules are fairly easy. So usually it requires around 3 steps. So let me come here. So for a Koch fractal, you need to start with a single segment like this. So this is our segment. So this segment has 2 points. It's a vector. So let's call this point 1. It has x1, y1, and we have point 2, initial x2 and y2. Okay, now so the first step is to divide this segment into 3 equal segments. So for example, let's say we want to divide it here and here. So now we get another 2 points. So let's just call this point P3 equals x3 y3. It's a vector, and you'll get another point. We'll call this P5. So I'll tell you why I call this P5. So it has x5 y5. Now this, so the lengths from P1 to for example P3, let's call it D. Let's call this D. So what happens is the lengths from P1 to P3 is equal to lengths from P3 to P5, and which is equal to from the length from P5 to P2, and we call this D. Sorry, D. Now after that, after this step, so we divide the segment into 3 equal points, and we find two new points, and finally we need to find the 4th point. So the 4th point, let's call it P4 here. So P4, which is x4 to y4. So this point P4, I'm sorry, okay. So this point P4, it will create an equilateral triangle from the point P3 P4 to P4 P5, and the length from P3 to P4 is again equal to D. So come here again, so length from P4 from P3 to P4 is equal to from the length from P4 to P5. So what that means is, since this is an equilateral triangle, the angle here, okay. Stroke. So this angle let's call it theta. This is equal to 60 degrees. Yeah. Okay. So this is basically the construction. Then what we do when we render it, we render the segment from P1 to P3, segment from P3 to P4, segment to P4 to P5, then again the segment from P2 to P5 or from P5 to P2, and we will not be rendering this segment from P3 to P5. So that's basically the construction. So it is very, very easy. Then this will create the Koch fractal. So to create the Koch snowflake, what we do is we will have 3 segments like this. Like this. That will create an equilateral triangle. And for each segment here, so for each segment, this one, for this segment, so for this segment, and for this segment, and also for this segment, we will be applying this rule recursively. So what happens is, for example, let's say if this is a recursive operation, so Koch fractal, so after some, so this is the first iteration. So in the second iteration, what we'll do is we will apply the rule, for example, for this segment, subsegment from P1 to P3. So it will be looking like this. And also this one will look like this, something like this. Yep. And this one also. Then after, in the third iteration, this segment will apply the these rules on it. So this is the like the basic rule. So what happens hopefully is like we'll get these infinite fractals, Koch snowflakes. So since we are rendering it on on the screen, we will have to limit the depth. We can't go into infinite depths because ultimately each segment will be, the dimension of the segment will be less than the pixel size for individual pixel size. So that's basically the operation. You can see like the rule here. So we have a segment, we divide it, subdivide each segment, then we'll get this snowflake. So I'll be using again C and Rayleigh. So I've already created my directory, and I have my make file. So now, so let's start. Let me include my basic libraries, eio.h. And my maths library today. Maths.h. Then finally, let's include Rayleigh.h. Let's define the let's call it screen width. Let's give it A40 by A40. I want it to be big. Let's create our main function. Window screen width by screen height, and our title will be, let's call it Koch snowflake. Let's set our target FPS to 30 is enough. Let's create our main event loop while window should not close. Let's go begin growing and growing. And this background. So let's make the background black. And finally, let's go window. Okay. Oops. Let's make. Okay, it compiled successfully. Let's run it. Okay, so we have a blank window. Okay, so now so what we need is we need to define some sort of segment type. So we need to represent our segment. So let me create a new type here. Let's call this a segment. So this segment it will have 2 points, so each segment can be represented by 2 points. So the first not points, actually 2 vectors. So the first vector, like for this example, for this segment we have vector p1 and p2, so each will have an x and y coordinate. So in Rayleigh we have already a type, it's called vector2 type. So vector2 type will hold let me close this. I think it's in opt. Yeah, so let's go to vector2. Yeah, so we have a vector2 type in Rayleigh already. So it has 2 values, a float x and y. So that's actually okay. So let's call our first point as a start for our segment, and let's put this end point. Okay, we have a segment. Now that means here we can represent our segment into points. So for example, let's create 2 points. Let's say vector 2. Let's call it point 1. So I want to draw a segment just to test in the middle of the screen. So let's say our x value. So our x value dot x for this vector. Now let's make the screen width divided by 2 minus let's say float segment length. Let's make it a 400 pixel length. So segment length by 2. So this is my x, and the y is screen height by 2. So point 2. Let's make this so basically I can make p1 dot x plus the segment length. So when I create segment, it can be, for example, can be represented by p1 and by p2. Okay, great. Now I want to render the segment here. So let's say create a function called draw segment. It will take segment and it will render it. So let me create a function here. So let's say void draw segment. It takes a type segment and it just basically draws it. So to draw a line, we have a draw line. I think we have a draw line function here already. So we can use this one because it takes vectors. We already have that. And also we can take this one, draw line ex, which draws a line using triangle. So we can give it a thickness on this one. So for now, let's just use, let's say, draw line v, and we use segment dot start, segment dot end, and let's give it a white color. Basically, there is a ray white color. There's this one. Okay, let's compile it, make clean and make. Yep, so let's run. Yeah, we can draw a line, so that works. Okay, yeah, so what's our next step now? Since we are doing this operation iteratively, that means we need a way to store like multiple vectors, segments. We need to have an array of segments because we'll be creating these segments recursively, and we need to store them somewhere and loop through that array or some memory location and draw them ultimately. So that means we need to have some way to store the segments. So we can allocate, just for example, create some fixed size array of some arbitrary number, or we can know. So what like one of the properties of Koch snowflake, that is given the number of iterations, that the depths of the recursive depths, we can know how many segments that can be created. So for a Koch snowflake, that means for a Koch snowflake where the initial position is we have 3 segments, the number of segments created is 3 times 4 to the power of n, where n is the iteration of the recursive depths. That means for a single line, we'll have this, it will not be 3, it's 1, so it will be 4 to the power of n. So if I have one line here, this line, if I only have like this one segment, and my recursive depth is, for example, 3, that means I create for each iteration I will be creating this 1, 2, 3, 4 segments. So if I have my iteration depth or recursive depth is 3, for each iteration I'll be creating 3, so that means 4 to the power of 3. Or 12 segments I'll be creating. But if my initial position, or when I start, I already have 3 segments, then it will be 3 times 4 to the power of n segments. So based on this, what we can do is we can create a let's define it here. So now I don't need this one, maybe I need this. Okay, so I can create any value, float, and I can call it number of segments. Let me make it small. Num segments. So my number of segments, I will be assuming I will have 3 initial position, is 3 times the power 4 to the power of n, or let's call it depths, max depths. So let's define this macro here. So what is max depth? let's make my max depth 1 for now. So this controls the recursive depth. So I have number of segments here, I know. So that means I can create, I know the number of segments for a given iteration or recursive depth. So that means I can create an array simply. So let's allocate it dynamically. I want to allocate dynamically. You can create it on the stack, but let me create. So segment, I'll have segments. This is an array, and let's allocate. So what is the size of our array is number of segments, and it's size of segment. So I have an array. So let me come here, and I don't want to forget. Let's free our segments here. So hopefully, so I have my segment here. Now what I want to do is I want to recursively create these segments from this formula here. So I want to create this segment. So our initial work is creating these points. So given point P1 and P2, I need to create point P3, P4, and P5. So how can we do it? So what that means, now I have a segment. So I have a segment. So I have a segment here, and I want to take these points, and from these points I want to create or find these 3 points. So let's call that function, let's call it let's make it void for now. Let's say it's create Koch points. So the new points is create new points, and this takes a point. So it takes vector 2, point 1, vector 2, point 2. So given point 1 and point 2, I need to find the value or new points. Basically, I want to create P3 and P4. Okay. So now I have P1, I have P2, and how could I find P3, P4, and P5? So now from, if you remember, these points from P1, P3, P3, P5, P5, P2 are all equal to D. And what D is for example, P3, it's a point where that divides this segment P1 to P2 into 3 equal points. So we need to find the length of this segment. So the length of this segment, so length of segment is, if for example it's straight in the x-axis, it is basically is x2 minus y2. But what happens is, let's say in later iterations, this segment might not be a straight line with respect to the x-axis or y-axis. For example, let's say this is our grid. Oops. Let's say this is our grid, something like this. This is our x and y. This is our origin point. This is my origin 0, 0. It might not be straight like this. If it is straight, then basically this segment length is straightforward. We just subtract the difference in the x-axis, but our line might look like this, for example. Okay, then to find the length of this segment, we just basically use the Pythagorean theorem. So we need to find this length, so we need to find the height, we need to find this length, and given this angle we can find the length of this one, but we don't need the angle to find the distance. We can use the Pythagorean theorem. That's basically, so if this is d, then d is the square root of for example a squared plus b squared, something like this. So let's come here. We have our Koch P1. Let's call it, let's find the hypotenuse. Yeah, that will give us the length of the segment. Let's call it hypotenuse for now. Plot hypotenuse. Hypotenuse is it like this? Let's go like this. Is the square root of the power, the difference between the p2 dot x minus p1 dot x squared plus again p2 dot y minus p1 dot y squared. So this will give us the hypotenuse. Now to find d, so d is the, so basically d, it just it divides this segment into 3 equal points. So we plot d is the hypotenuse divided by 3 is the point that divides it's basically that's the length. It's 3 times. So we have 3 d's for the segment. So d is the hypotenuse divided by 3. Okay. Now we have d. So if we have d, we know position P3. So what's point P3? We know what point P3 is. So point P3 will be in the x-axis. It will be point P1 dot x plus d. And in the y-axis, it will have some component. So we need to find the x and y components of d. We need to find that. So again, from the what we have, so if we got this value, so we have this the hypotenuse. Let's call it it's confusing actually. This should not be d, this should be the hypotenuse. It should be less because I call it the hypotenuse here. I call it the hypotenuse, and I've already said that d. So if we have this one, and if we know the angle here, yeah, if I know the angle here, and if I know this value, the length of the hypotenuse, then I can find this, the distance from this point to this point, and the distance from this point to this point. Let's call this capital X, and let's call it capital Y. So what happens is, so again, like we can use basic trigonometric function. So x, capital X, this is capital X, will be d times the cosine of that angle theta, something like this. And capital Y will be d times the sine of that theta. Okay, so okay, now that means we need to find the value for theta. Okay, theta for this line, the angle for this segment. So finding theta is actually easy. Sorry, this thing. So this is my segment, let's say, and we have the hypotenuse. I want to know the x and y component of that point D. So D is something here. So D is the point that divides this segment into 3 equal points. So it will be P3. this will be P5, and this will be P2, something like that. So now float angle is, I can find the angle here, theta. So by calculating the height and the width of the triangle of the segment. So that means I can say in C there is a function called arctan to F, tan to F, and it is that means the angle theta is equal to the arctan, or the inverse tan of the height divided by the width of the triangle. So the height of the triangle is P2 dot y minus P1 dot y, and comma the width is P2 dot x minus P1 dot x. So this is our angle. So we know D. So we know the length of the segment, the initial segment between P1 and P2. We know the angle with respect to the origin. Now we know D, the length D. So D will give us the point P1, and D will give us the point where the length of the segment that will divide it, the original segment, to 3 equal positions. So what we need to do is we need to find the x and y component of this D. So float the x, quite something like this, let me do, is to be D times the cos f of the angle. So what we need to know is in C the angle is given in radius. So we need to consider this, and our YD is sine of the angle. So I know the x and y component of this D. This is very cluttered now. I think I need to clean it. Yep. Yeah. So I know this D, the length of this D. Now I know the x and y component. That means the x and y component, the width and the height of the D, if for example it's tilted. So what this will give me, I can use the x and y component of D to find x3 and y3 of points, let's say P3. So that means now I can create a segment, no, not actually a segment, a vector called P3. So it has a dot x and dot y. So what is the x value for D is, it's P1 dot x plus this P. So if this is x and this is D, so point P3 in the x direction is this x1 plus x3. Again, the y will be P2 dot x, P1 dot x dot y plus y of D. So this gives me what's P4, P3. Now to find P5, because let's find P5, because P5 is easier, because P4 needs rotation, we'll handle later. So P5, so it's easy to find P5 because the length between P3 and P5 is also D. So that means we can again use, that means P5 means P1 to find the x component. X5 means x1 plus 2 times D. what happens is to find the point P5, we can say P1.x times xd times 2. Again, for this case, we can say times 2. Now, this is a bit tricky part is to find vector P4, because vector P4 requires some kind of rotation. So again, what we need to consider is this length, again from P3, point P3 to P4 is D, but now it is rotated 60 degrees by 60 degrees. So what we want to do is, the trick here is we need to find this vector D. So we have already calculated it previously, and rotate this vector by 60 degrees, and now add it to P3. So rotate this vector and add it to P3. So how do we rotate a vector? So vector rotation, rotate a vector. Okay, so to rotate a vector, we can employ something called a rotation matrix. So what you can do is, if we have, for example, here a point like a vector that has an x and y components. So for example, the vector, previous vector that we want to rotate has the values x and y, and the new point or values after it has been rotated by this theta degrees will be for the x coordinate will be x cos theta, x times cos theta minus y times sin theta, and for the y, these are the new positions, are x sine times sin theta plus y times cos theta. So in our case, what we want to do is we need to rotate this D, okay, this D vector, and add the rotated vector to the point P3. So basically what we are trying to do is, when we are rotating a vector, we are rotating it with respect to the origin. On this graph, for example, with respect to the origin, what we are measuring the angle of like a segment, this for example, based on this, based on the origin. So but what happens here is, when we are trying to rotate this, for example, this point in 60 degrees, we want to consider, we are measuring our like our reference is not the origin of the graph, or for example our grid in the image, but rather our reference is this vector. So we need to measure 60 degrees with respect to this vector, not this one. So that's why we are adding, what we are basically doing is we are changing the origin. So changing the reference origin and bring it here, moving it to this position. So to do that, what we are trying to rotate is, let's call it our pivot is our D, which is already defined by X, Y, and D. So what you can do is you can create a vector and call it a pivot. Okay, and it will take vector 2, and its X value is XD, and its dot Y value is YD. So now what happens with P4 is we pass it to some function, rotate, let's call it vector. So here we pass in 3 values. The first value is the vector P3. The second value is our pivot vector. Third value is our angle. Okay, so let's give our angle something like this. So our angle is by default, so each vector is rotated by 60 degrees, so they will create an equilateral triangle. So we already know our angle. So now what happens is this angle is where I'm passing it by degrees. Angle in degrees. So we need a way to convert it to radians. So let's create a function that will return a float. Let's call it degree to rad. Okay, so it will take in a degree, angle in degree, let's call it the angle, and it will return the value in radians. So to convert degree to radians, what we need to do is we need to multiply the angle times pi divided by 180 degrees. So this is the formula for converting degrees to radians. Now, so what we do is let me create a function that will return a vector, and let's call it rotate vector. So it takes vector to a p, vector to a pivot, and float angle. Okay, so using this rotation formula, we need to rotate the vector. So our new x and y position, so float x, our new x position will be our pivot dot x times cos of the angle, but the degrees, the radians, so let's call it degree to radians angle. Then it is minus pivot dot y times sine of degree to radians. So our y will be this times sine f. So this will be plus cos f. Okay, so we have rotated this pivot, but now what we want to do is we need to add that rotated pivot, add it to P3. So what we do is we'll be extending it. So I rotated this vector, this G, by some 60 degrees, and I shifted it. So the origin will be P3. So I need to come here and I need to add p dot x plus p dot y plus where is it? Okay, p like this. And let me create a new vector. Let's call it p4, which is a vector 2. So now the dot x will be x and the dot y will be y. And let's return p4. Okay. So now p4 will be pivot rotated by 60 degrees and added to P3. That means the origin will be the P3. So in images, usually the origin is in the top left corner, so we need to rotate it by negative 60 degrees here. Okay, so now I have P4. This seems okay. I have P3 I have p5, I have p4, but now the issue is this function is not returning, so that means I need to update these values somewhere. I want to call them somewhere. I want to pass p1 and p2, and I want to update. So I want to, let's say, just pass these values as a so I want them to be passed as a reference somewhere there. So these points are, because this is a recursive function, hopefully I want to update or calculate the values of p3 and p4. So I want this to be p4, let's make them p4 vector p5. So that means now p3 is this, p4 is this. Okay. Okay. So what I'm trying to do is, let's say for example here I create vector 2 p3 p4 p5. Okay. P3 p4 p5. Then I need to say I need to create the other points by passing p1 p2, and I pass this p3 p4 and p5 by reference, something like this. So this will give me the value for point p3 p4 and p5. So hopefully this let's try. This will give me 3 other segments. So let's say for segment segment 2, segment 3. So I have segments. So my new segment would be from p1 to p3, from p3 to p4, from p4 to p5, and from p5 to p2. So for example, my second segment would be from p1, first segment would be from p1 to p3, from p3 to p4, and from p4 to p5, and final segment from p5 to p2. Okay. Yeah, so let's just let me do something like this. So now I want to test it. So row segment 1, row segment 2, row segment 3, and row segment 4. Does it work? Let's see. Oops. So this should be multiplied times passing vector. Okay. Bring passing to rotate. So this is a pointer, so I need to send the value like this. Okay, unknown vector 2 point line 33. Oops. This vector 2. Another point here. Assign to vector 2 following compact vector 2. Take that as line 43. That is GG. So I think I need to the value of P3 and value of P4. Okay, segment length. So okay, delete segment length. Let's say segment. Let's make this 300. Another. Oops. Segment length. Oops. Okay, and this is segments. Okay, variable P3 is declared here. Oops. Create this is here. Let's try. Yeah. Okay. So that means this is my first segment now. My initial segment was from here to here. Now I have 4 segments. 1, 2, 3, 4. Okay. Great. Okay. So now what we want to do is we need to now create this recursively. So I have already can create the points. So if I can create the point, that means I can now create my segment recursively, add them to my array, and loop. So rather than like drawing each segments individually, I can put them in the array and loop through the array and draw them. So what I want to do is I need to create a new function, void, and I want to create Koch. Yeah, I need to create a Koch. I'm gonna call it Koch fractal. So my Koch fractal will take my segments, my array, and also I need my points, my vector 2, P1. Let's make the order like this. So I take my 2 points, vector 2, P2. Then I take my segment array, and I want to track what is the element count. So initially my array is empty. When I put a segment into the array, I need to count it. Well, that means I need something global. So int, I need something that I can pass. as a reference, they call it my segment count, and I need a value that control the depths. What is my current, because this function is a recursive function, so I want to know what iteration I am in. Let's call it, since I have max depth here, let's call it depths, the current depths. This will tell me the current depths. Okay, now what this does, it's something like this. I just need to copy this and put it here. So I have this and I create the points. Okay, I have my points. Then for each new point, now because this is recursive, for each new point, okay, so I have segment. Let's say I will be having a segment from P1 to P3, and for segment P1 to P3, again I want to create another segment. So I need to call this function again, but now on different points. That means now I'll be calling the create Koch fractal for each individual segment. So in my case, I'll be calling, for example, for segment P1. So from segment P1 to P3, again I'll pass in segments. Then my segment count, so this I will not be updating it here, but now what happens is my depths will be incremented. Depths so I need to do this 4 times. So for segment P1 to P3, then I have for segment from P3 to P4, for segment P4 to P5, and for segment P2 to P5. Now what we need to do is we need to have an exit condition. Otherwise this recursion will go on forever. So when should we stop? We need to stop this iteration when the depths has reached the max depths. Okay, so if depths equals max depths, okay, when the depth is equals to the max depth, like for a given segment, number one, what we want to do is we need to add that segment. Okay, we need to add that segment. That segment value is seg count, so we are getting the value. I'm doing here seg count. So what I'm doing here is I'm getting the value pointed by the pointer seg count. So this is a new segment. I create a segment, and that segment has a start, which is P1, and an end, which is P2. Okay. After that, I need to increment. So I need to increment the value again pointed by the pointer seg2. Okay, the value pointed by seg. Then I need to return out of the loop. Hopefully this works. So I have depth in depth is equal to depth. I need to add to segments, increment segment count, and return. Okay, I think this will work. So now what happens is I have these points. Now I need to call this create Koch fractal. Koch fractal. Oops. Create Koch fractal to P1, P2. So where is my Koch fractal? P1, P2. I already have P1 and P2. Our segments array, my seg count, which I don't have for now, and my depths, something like this. So let me create two variables. So first is the int seg count. Let's create seg count, which is currently 0 segment. And depths again, which is 0. Okay, now we need to modify this function. So previously we are drawing a single segment, but I want to draw all the segments in the array. So let's make this draw segments and passing segments. So if we go here and modify this again, and this will take an array, and I need to know the size. So I'm int num segments. What is we want to do is for int I equals 0, I is less than num segments, increment I, and we need to draw segment I, segment I int, segment. Yep, this is what we want to do basically. So here we need to pass in the num segments, total number of segments. Let's check if the function is running. So we have some errors. Undeclared function segments, segments. What? Oh, segments. Oh, where is it? Oh, this should be segments. Pointer conversion int. Again, I have some errors. Incompatible. Integer to pointer conversion. Oh, okay. Yeah. This is a pointer, so I need to pass in the address. What I want to do is in seg count, I need to pass the address of this function here. Okay, num segments, draw segments, etc. Oops. Where is it to? Again, let's try again one last time. Yep, let's run it. Oops, so we have some memory error. For since our depth is 2, Yeah, I mean 16. You have 16. Let's check it. Yeah, okay. So no, for each segment we have 1, 2, 3, 4. Now we have like this 4 other segments. So we total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So we have 4 squared. If I increase this to, let's say, 4, it's from Koch. Yeah, so basically we have created the Koch fractal. Now, if we want to make the Koch snowflake, this snowflake, I need to create an equilateral kind of triangle as my initial point. So what I can do, we have these points. So now my point is a screen width, so it's in the middle of the screen. Let it be, but now I need a vector 2.3. So I'm trying to create something like this. I have P1 here, so this is P1. I already have P2. Now I want to create P3. Now the length of this segment is all equal, so that means we can find this value. Because this is an equilateral triangle, we know this angle, this is 60 degrees, and we know this size, and we know that. So if, let's say, this is capital D, then this is D over 2, or we know this is again capital D, we know theta, so that means we can find this x and y value only from D and theta. That means again, like same, y is the D times the sine of theta, and x is the cos of theta. I can use that. So we know the D is the segment length, so P3. Vector 2 so the x is d times cos of degree 2 rad of 60 degrees. Yeah, that's the x, and I need to add this to P1, so P1 dot x plus this. The y is yeah, it's again P1 dot y plus d times a sine of degree 2 rad of 60 degrees, I guess. I have these 3 points, and I want to calculate the Koch fractal for the segment P1, P2, and another for the segment P1, P3, and another for the segment P2 to P3. Let's make this 0 and let's check if everything is working. So oops. Sorry. This is a segment like this. Okay, yep. Yeah. Okay, that's upside down. That means I need to change this angle. So this angle needs to be minus 60 degrees. Minus 60 degrees. Let me close this. Let's check. Okay, so now let's increase the steps to 1, let's say. Okay. Yeah. Okay, there's something here. Add rotates by negative 60 degrees. This 60 degrees. What happens if I make this? Let's check. Okay. No, I think the issue is here. So from P1 to P2, from P1 to P3, let's make this from P3 to P. No. Let's make this P3 to P2. I think this is the issue. Okay, but I don't know. Okay, so P1 to P3, P3 to P2. Okay. I think the issue is here. So from P1 to P2, from P. Okay, let me go like this. From to P1 to P2, from P2 to P3, and from P3 to P1. I'm not sure what's happening. Code is working, but okay. So that means there's something wrong with the order, and I can fix that by now. I can make this positive and ensure it will work. But I'm not sure why. Okay, it's inverted, but okay. Okay. So let me do this. Let me increase this depth to 4. Let's check. Yeah, it works, but I'm not sure why it is I'm not sure what I did wrong here. I think the order, there is something wrong. Is it, am I going, should I say from P2? Okay, it works anyways. So what we see here is by changing the angle, we can find the other version of the Koch fractal. It's called the Koch antifractal. Where is it? Yeah, the anti-snowflake. Okay. So the fascinating thing about these Koch snowflakes is when we change the angle of rotation, we get the anti-snowflakes. So which are the snowflakes, the angles are now opposite. So let's make it 16. So these are the snowflakes, and the previous one, they are the anti-snowflakes. So basically this is the construction, like steps required to construct the Koch snowflakes. I hope you find the video interesting, and so that's it. Thank you for watching. Bye.